What if the atmosphere above your head is starting to lose its balance? Right now, high above the Earth, the jet stream, a powerful river of air that controls weather across the northern hemisphere, is bending, slowing, and becoming unstable. And when that happens, storms stall, cold air plunges south, heat waves intensify, and weather systems can lock into place for days. Over the next 10 days, parts of the United States could experience some of the most chaotic atmospheric patterns of the season. But this isn't science fiction. It's real atmospheric physics happening right now. In this video, we're going deep into the hidden mechanics of the jet stream, the polar vortex Rossby waves, and why the atmosphere may be entering a prolonged unstable phase. If you enjoy cinematic science documentaries and realistic weather visuals, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss future episodes. Now, let's go high above the Earth and see what's happening in the atmosphere. High above the Earth, in the upper reaches of the atmosphere, a narrow band of fast-moving air flows around the planet in a continuous path. This band, known as the jet stream, forms near the boundary between the lower atmosphere and the layer above it, where temperatures shift sharply across latitude. It exists at altitudes where commercial aircraft sometimes travel, but it is not a still environment. It is a dynamic river of air shaped by differences in heat between the equator and the poles. The air within it moves from west to east in broad waves, guided by the rotation of the planet and the uneven distribution of solar energy. The jet stream is not a single line, but a series of corridors that wrap around the globe. These corridors are strongest where the contrast between warm and cold air is most pronounced. Warm air rising from lower latitudes expands upward and outward, while cold air from polar regions sinks and becomes denser. This imbalance creates pressure differences that accelerate winds high above the surface. The result is a fast-moving current that can reach speeds of several hundred kilometers per hour in certain regions, although its strength changes over time and location. At this height, the air is thin and dry and clouds are often absent, leaving the flow invisible to the human eye. Its presence is inferred through weather patterns and the movement of storms below it. Satellite observations from agencies such as NASA and other meteorological organizations reveal its structure as a shifting ribbon encircling the hemisphere. This ribbon is not smooth. It bends and curves as it responds to changes in temperature terrain below and the interaction of large-scale atmospheric systems. The formation of this high-altitude wind band is tied to the way Earth receives energy from the sun. The equatorial regions absorb more direct sunlight, warming the air and causing it to rise. Near the poles, sunlight arrives at a lower angle, spreading its energy over a larger area and producing colder conditions. The atmosphere attempts to balance this difference by moving heat from warmer regions toward colder ones. The jet stream becomes one of the main pathways for this energy redistribution in the upper atmosphere. In this outer atmospheric region, motion is influenced by the Coriolis effect, a force that arises from the rotation of the planet. As air moves from high pressure to low pressure, it is deflected, shaping the west to east flow that characterizes the jet stream. This deflection does not create the wind itself, but organizes its direction, giving the global circulation its familiar patterns. Without this influence, air would move in more direct north to south paths, and the structure of the jet stream would not form in the same way. The jet stream sits near the tropopause, a transitional boundary between the troposphere below and the stratosphere above. This boundary acts like a lid limiting vertical movement of most weather systems. Below it, cloud storms and precipitation develop. Above it, the air becomes more stable and layered. The jet stream flows along this boundary where temperature gradients are strongest, maintaining its position as a response to both thermal contrast and atmospheric layering. Seasonal changes alter the strength and position of this wind band. During colder months in the northern hemisphere, the temperature difference between polar and tropical regions increases, often strengthening the flow. In warmer months, the contrast weakens, and the jet stream can become less intense and more variable. These shifts are gradual but continuous, reflecting the ongoing adjustment of the atmosphere to changing solar input throughout the year. The structure of the jet stream also includes long wavelength undulations known as Rossby waves. These waves are large bends in the flow that extend thousands of kilometers across the hemisphere. They develop as a result of the conservation of energy and momentum in a rotating system. As the jet stream moves over different surfaces, including oceans and continents, these waves can grow or shrink, altering the path of air masses below. At this outer level of the atmosphere, these patterns remain smooth but constantly evolving, never fixed in place. Although invisible, the jet stream plays a central role in organizing weather patterns across the globe. It guides the movement of storm systems, influences temperature distribution, and affects the timing of atmospheric changes at the surface. Its position can determine whether regions experience calm conditions or active weather sequences. Even small shifts in its path can lead to noticeable differences in weather over large areas. In this upper atmospheric environment, the flow remains in constant motion, responding to the balance of heat rotation and pressure. It is a system without a fixed shape, yet it maintains a recognizable structure through the forces that sustain it. The air continues to circulate along its path, linking distant regions of the planet through a continuous exchange of energy and momentum. Above the jet stream, the atmosphere gradually changes in character as altitude increases and the air becomes thinner, colder, and more stratified. In this higher region, the stratosphere begins to dominate a layer where temperature no longer decreases steadily with height, but instead becomes more stable, and in some places increases. Over the polar regions, this structure becomes especially important because it influences the stability of air masses far below. The polar stratosphere forms a cold reservoir of air that sits above the lower atmosphere and interacts with global circulation through slow but persistent exchanges of energy. In this polar stratospheric region, sunlight is weak for long periods during seasonal cycles, especially in winter when the sun remains low or absent for extended intervals. The lack of solar heating allows extreme cold conditions to develop. Temperatures in this layer can drop far below those in the surrounding mid-latitude stratosphere, creating a strong thermal contrast between polar and tropical regions at high altitude. This contrast plays a role in shaping the balance of winds beneath it, including the jet stream. The stratosphere above the poles is not a uniform mass of cold air. It contains variations in temperature density and chemical composition that shift gradually over time. One important feature is the presence of ozone, a molecule that absorbs ultraviolet radiation from the sun. Ozone is not evenly distributed, and its concentration influences how heat is absorbed in the upper atmosphere. When ozone levels and solar input interact, they produce subtle heating patterns that modify the stability of the surrounding air. During extended periods of polar darkness, the absence of solar radiation allows the stratosphere to cool further. This cooling strengthens the vertical temperature gradient between the stratosphere and the layers above and below it. As the air becomes colder and denser, it tends to settle into a more stable configuration, reducing vertical mixing. This stability can act as a controlling influence on atmospheric motion beneath it, because energy transfer between layers becomes less efficient. The polar stratosphere also plays a role in organizing large-scale circulation patterns through its relationship with pressure systems. A persistent low-pressure feature often forms over the polar regions in the stratosphere, driven by temperature differences and the dynamics of rotating air. This feature is part of a broader system that includes the polar vortex, a circulation pattern that encircles the pole and helps contain cold air within high latitudes. Although the vortex exists across multiple layers, its structure in the stratosphere is particularly stable and influential. When the polar stratosphere remains cold and stable, the circulation within the polar vortex tends to strengthen. Stronger circulation keeps cold air more tightly confined to polar regions. This confinement affects the temperature gradient between the pole and lower latitudes. The stronger the gradient, the more energy is available to drive winds in the lower atmosphere. This connection links the conditions of the polar stratosphere to the behavior of the jet stream far below. At times, however, the polar stratosphere can experience disturbances that alter its usual stability. These disturbances often originate from upward propagating waves in the atmosphere below. As these waves rise, they transfer energy and momentum into the stratosphere, where they can disrupt the balance of the polar circulation. When this occurs, the structure of the polar vortex can weaken, and temperature patterns can shift over relatively short periods. Such changes in the polar stratosphere do not remain isolated. Because the atmosphere functions as a connected system, alterations in one layer influence others through vertical coupling. When the stratospheric circulation weakens, the distribution of pressure above the poles changes. This change modifies the exchange of energy between layers, allowing effects to propagate downward over time. The jet stream in the upper troposphere responds to these adjustments through shifts in its position and strength. The temperature structure of the polar stratosphere is also influenced by seasonal cycles. During transitions from winter to spring, sunlight gradually returns to high latitudes, introducing new energy into the system. This warming is uneven and can lead to shifts in the stability of the stratospheric air. As temperatures rise, chemical and dynamic processes interact, gradually transforming the structure of the polar circulation. These transitions occur over weeks and months, reflecting the slow adjustment of the atmosphere to changing solar conditions. Chemical composition in the polar stratosphere contributes to its behavior as well. Ozone interacts with ultraviolet radiation, absorbing energy and redistributing it as heat. In regions where ozone concentration is higher, localized warming can occur. In contrast, areas with lower ozone levels remain colder. This uneven distribution creates gradients that influence the movement of air within the stratosphere. Over time, these gradients contribute to shifts in circulation patterns that extend across large areas. The polar stratosphere also interacts with the lower atmosphere through the exchange of planetary scale waves. These waves originate from variations in surface conditions such as land, ocean, and topography. As they move upward, they can either strengthen or weaken depending on atmospheric conditions. When they reach the stratosphere, they may break or dissipate, releasing energy into the surrounding air. This process can alter the balance of forces that maintain the polar circulation. In stable conditions, the polar stratosphere acts as a relatively contained layer with slow and predictable motion. In more dynamic conditions, it becomes a region of active interaction, where energy is redistributed across scales. These variations influence not only the polar regions, but also the broader atmospheric system, including the winds that shape weather patterns at lower altitudes. The connection between the polar stratosphere and the rest of the atmosphere is continuous but indirect. Changes occur gradually and propagate through layers over time. The cold reservoir above the poles therefore serves as both a stabilizing and responsive component of the global circulation system. Its state reflects the balance of energy entering and leaving the polar atmosphere, and its behavior contributes to the structure of winds far below. As this high-altitude region maintains its cold and layered structure, it continues to influence the flow of air across the hemisphere through subtle adjustments in pressure and temperature. These adjustments form part of a larger atmospheric balance that links the upper and lower layers in a continuous cycle of movement and exchange. Below the stratosphere, the atmosphere becomes denser and more active in vertical motion, forming the troposphere where most weather processes occur. This lowest major layer extends from the surface of the Earth upward to a height that varies by latitude, being higher near the equator and lower near the poles. In this region, air is constantly mixing, rising and sinking in response to heating from the surface. Solar energy absorbed by land and ocean warms the air above it, setting in motion the fundamental circulation that connects directly to the behavior of upper-level winds. In the troposphere, pressure decreases steadily with height, creating a vertical gradient that drives upward motion when air near the surface becomes warm and less dense. As this air rises, it expands and cools, eventually forming clouds when moisture condenses. This process is continuous and forms the foundation of weather systems. The energy that drives these motions originates primarily from uneven heating of the Earth's surface, which varies with latitude, surface type, and time of day. The lower atmosphere is highly sensitive to changes in surface conditions. Land heats and cools more rapidly than water, creating temperature differences between continents and oceans. These differences generate pressure gradients that initiate wind. As air moves horizontally from high pressure to low pressure regions, it begins to organize into larger patterns of circulation. These patterns are not isolated. They extend upward and interact with the structure of the upper atmosphere, including the jet stream above. Within this layer, convection plays a central role. Convection is the vertical movement of air driven by temperature differences. Warm air rises because it is less dense while cooler air sinks. This continuous overturning creates a dynamic environment where energy is constantly redistributed. In regions where moisture is present, rising air can lead to cloud formation and precipitation. These processes are closely tied to the energy balance of the planet, as they help transfer heat from the surface into the atmosphere. The troposphere also contains boundary layers near the surface where friction with terrain slows down wind movement. Mountains, forests, oceans, and urban regions all influence how air moves close to the ground. This frictional effect reduces wind speed and alters direction, creating localized patterns that can differ significantly from conditions higher above. As altitude increases within the troposphere, this friction decreases, allowing winds to accelerate and become more organized. At higher levels of the troposphere, the air becomes more stable compared to the turbulent lower regions. This upper portion is where the jet stream forms, influenced by strong horizontal temperature gradients. The transition between the lower turbulent air and the more organized flow above is gradual, shaped by changes in temperature, pressure, and humidity. These gradients are strongest between tropical and polar air masses, where contrasting temperatures create strong pressure differences. The distribution of heat across the surface of the Earth is uneven. Near the equator, sunlight strikes more directly, producing higher temperatures and stronger upward motion. Near the poles, weaker sunlight results in cooler air and reduced vertical movement. This difference creates a large-scale circulation pattern that drives air upward in warm regions and downward in cold regions. The upper return flow of this circulation contributes to the formation of high-altitude winds. Storm systems develop within the troposphere as disturbances in pressure and temperature grow and interact. These systems can range from small localized cells to large rotating cyclones spanning hundreds of kilometers. They are guided by the prevailing winds aloft, which are influenced by the jet stream. As storms move, they transport heat and moisture across regions, redistributing energy in a continuous cycle. Water vapor is a key component of this layer. It carries latent heat energy stored in phase changes between liquid and gas. When water vapor condenses into clouds and precipitation, this energy is released, fueling further atmospheric motion. This release of energy contributes to the development and intensification of weather systems, linking moisture processes directly to atmospheric dynamics. The structure of the troposphere is not static. It changes with seasons, latitude, and time of day. During warmer periods, convection becomes more active, and the layer can expand slightly. During colder periods, it contracts and stabilizes. These changes affect the height of the tropopause, the boundary between the troposphere and the stratosphere. The position of this boundary influences how energy and momentum are exchanged between atmospheric layers. Large-scale pressure systems in the troposphere interact with upper-level winds in complex ways. When pressure systems align with jet stream patterns, they can reinforce or weaken flow. This interaction determines the paths of storms and the distribution of weather across continents. In some cases, slow-moving pressure systems can become trapped beneath certain jet stream configurations, leading to prolonged weather conditions in one region. The lower atmosphere also responds to surface temperature anomalies. Warm ocean regions can enhance evaporation and convection, while cold regions suppress them. These variations influence atmospheric stability and can alter circulation patterns over time. Because the atmosphere and surface are connected through continuous exchange of heat and moisture, changes in one component affect the other. As air rises through the troposphere and approaches the upper boundary, it begins to encounter more stable conditions that limit further vertical movement. This transition marks a shift from turbulent motion to more organized flow. The energy from surface heating is redistributed horizontally, contributing to the formation of strong upper-level winds that encircle the planet. The troposphere serves as the primary engine of weather, driven by solar energy and shaped by Earth's surface diversity. Its motions extend upward into higher layers, linking surface processes with global circulation patterns. Through continuous movement of air heat and moisture, it forms a dynamic system that connects directly to the structure of winds above, maintaining the balance between energy input and atmospheric response. Across the planet's middle latitudes, the atmosphere is shaped by a persistent imbalance between warm tropical air and cold polar air. This imbalance forms a broad zone where temperature changes sharply over relatively short distances. In this region, the gradient between heat and cold becomes one of the primary drivers of upper-level wind strength. Air attempts to redistribute energy from warmer areas toward cooler ones, and in doing so, it organizes into large-scale flow patterns that extend through the upper troposphere and influence the jet stream above. Temperature gradients in this middle latitude region are not uniform. They vary with season surface conditions and ocean currents. During colder months, the contrast between equatorial warmth and polar cold intensifies, strengthening the horizontal temperature difference. This increased contrast enhances pressure differences aloft, which in turn accelerates wind speeds at higher altitudes. During warmer months, the gradient weakens, leading to more irregular and shifting flow patterns. The atmosphere responds to these gradients through large-scale adjustments in pressure distribution. Warm air expands and rises, creating zones of lower pressure near the surface and higher pressure aloft. Cold air contracts and sinks, forming the opposite pattern. These opposing motions create a dynamic balance that drives horizontal movement of air. At higher altitudes, this movement becomes more organized, forming fast-flowing currents that encircle the hemisphere. Within this middle latitude belt, air masses from different origins frequently interact. Tropical air masses are typically warm and moist, while polar air masses are cold and dry. When these air masses meet, they do not mix immediately. Instead, they form boundaries where strong gradients exist. These boundaries are regions of instability that can generate waves and disturbances in the flow. These disturbances extend upward into the upper atmosphere, influencing the structure of the jet stream. The energy available in this region is continuously redistributed through atmospheric motion. As air flows from high pressure to low pressure areas, it carries heat with it. This transport of energy is not smooth or uniform. It occurs through evolving patterns of circulation that shift over time. The result is a constantly changing environment where no single configuration remains fixed for long. The middle latitudes are also influenced by the rotation of the planet, which deflects moving air and shapes the direction of large-scale winds. This deflection organizes flow into predominantly west to east movement at higher levels of the atmosphere. The interaction between rotation and temperature gradients produces conditions favorable for the development of strong upper-level currents. In this region, large atmospheric waves known as Rossby waves begin to form more clearly. These waves arise because the atmosphere seeks equilibrium but is constrained by the Earth's rotation and uneven heating. As air moves poleward and equatorward within these waves, it creates alternating zones of high and low pressure. These alternating zones influence the position and shape of the jet stream above, causing it to bend and shift. The structure of these waves is not fixed. They grow and decay depending on the strength of temperature gradients and the energy present in the system. When gradients are strong, the waves can become more pronounced, extending far north and south. When gradients weaken, the waves tend to flatten, leading to a more zonal flow, where winds move more directly around the planet. Storm development in the middle latitudes is closely linked to these wave patterns. Disturbances along temperature boundaries can grow into larger systems, as energy is transferred from the environment into organized motion. These systems draw energy from the contrast between warm and cold air, intensifying as they move along the flow guided by upper-level winds. The jet stream plays a central role in steering these systems, determining their paths and evolution. The interaction between surface conditions and upper-level circulation is continuous. Changes in ocean temperatures, land heating, and atmospheric moisture all contribute to variations in the strength of temperature gradients. These variations influence the formation of waves and the organization of wind patterns above. The system responds, gradually adjusting over days and weeks as energy is redistributed. At higher levels within the middle latitudes, air becomes increasingly influenced by large-scale pressure systems. These systems can persist for extended periods, shaping regional weather conditions. When aligned with upper-level flow patterns, they can either reinforce or disrupt the jet stream. This interaction determines whether the flow remains smooth and fast or becomes more meandering and fragmented. The middle latitude region acts as a transition zone between tropical and polar circulation systems. It is here that energy transfer between these two regions is most active. Warm air moving poleward and cold air moving equatorward create a continuous exchange that drives atmospheric motion. This exchange is not balanced at every moment, but over time it maintains a global equilibrium in energy distribution. As air continues to move through this region, it gradually feeds into higher altitude currents. The organized flow that develops here contributes directly to the structure of the jet stream above. Variations in temperature gradients, wave patterns, and pressure systems all combine to shape the strength and position of this upper-level wind band. The middle latitudes therefore function as a critical zone of atmospheric transformation. Energy enters from surface processes, is reshaped through circulation, and is transmitted upward into faster-moving currents. This layered interaction connects surface weather to global wind systems, maintaining a continuous exchange that defines the behavior of the atmosphere at multiple levels. Within the upper troposphere, where the air becomes thinner and the influence of surface friction fades, large-scale atmospheric waves take on a more defined structure. These waves, known as Rossby waves, arise from the interplay between Earth's rotation and the uneven distribution of heat across the planet. In this region, the waves are not abstract features, but physical undulations in the flow of air, shaping the path of high-altitude winds as they circle the hemisphere. Rossby waves form because air moving north and south experiences changes in the apparent force created by Earth's rotation. As air shifts toward the poles, it tends to be deflected in a way that creates curvature in its path. As it shifts toward the equator, it bends in the opposite direction. This repeated adjustment produces a wave-like pattern in the atmosphere. These waves are not stationary. They travel, amplify, and weaken depending on the surrounding energy conditions. In the upper troposphere, these wave structures interact strongly with the temperature gradient between polar and tropical air masses. Where the gradient is strong, the waves become more energetic and elongated. Where the gradient weakens, the waves flatten, and the flow becomes more uniform. This relationship links the shape of atmospheric waves directly to the distribution of heat across the planet. The jet stream flows along the boundary of these wave patterns. Rather than following a straight path, it bends northward and southward in response to the evolving shape of the waves. These bends are not random. They reflect the underlying balance of forces within the atmosphere, including pressure differences, temperature contrasts, and rotational effects. As a result, the jet stream becomes a visible expression of deeper atmospheric structure. In this region, air movement is dominated by horizontal flow rather than vertical motion. The strong temperature differences between air masses create a layered structure in which warm air tends to rise and move poleward aloft, while cold air moves equatorward. This exchange occurs continuously, forming a circulating system that redistributes energy across the hemisphere. The waves in the upper troposphere can extend over thousands of kilometers. Their size and shape influence the movement of weather systems below. When waves become amplified, they can create deep troughs of cold air and strong ridges of warm air. These features alter the paths of storms and determine where weather systems intensify or weaken. Energy transfer within these wave structures is gradual but persistent. As air moves along the curves of the wave, it carries heat and momentum from one region to another. This transport is not uniform. It varies depending on the strength of the flow and the surrounding atmospheric conditions. Over time, these variations lead to changes in the overall configuration of the jet stream. The upper troposphere also serves as a region of interaction between different scales of motion. Small-scale disturbances such as localized turbulence can merge into larger patterns when conditions allow. Conversely, large wave structures can break down into smaller eddies when energy is dissipated. This continuous transformation of scale is a defining characteristic of atmospheric dynamics in this layer. Temperature differences remain the primary driver of motion in this region. Warm air rising from lower latitudes spreads outward at high altitude, while cold air descending from polar regions spreads toward lower latitudes. These opposing flows meet along boundaries where wave activity is most pronounced. The resulting patterns are dynamic and constantly shifting. The structure of the jet stream is closely tied to these processes. It forms along the strongest gradients in the upper troposphere, where the contrast between air masses is greatest. As Rossby waves evolve, they guide the jet stream into curved paths that reflect the underlying energy distribution. The jet stream does not exist independently of these waves, but is embedded within them. At times, the waves can become highly amplified, leading to large northward and southward excursions of the jet stream. These amplified patterns can persist for extended periods, depending on the stability of the surrounding atmosphere. During such periods, the flow becomes more irregular with alternating regions of strong and weak wind speeds. The interaction between waves and the jet stream also influences the movement of energy across the hemisphere. As air follows the curved paths of the flow, it transports heat into regions that would otherwise remain colder. This redistribution helps maintain the overall balance of the climate system, even as local conditions vary widely. In the upper troposphere, the balance between order and variability is continuous. The atmosphere maintains a general structure while allowing for constant change within that structure. Waves form, evolve, and dissipate, but the overall circulation remains intact. This balance is maintained through the continuous exchange of energy between different regions of the planet. The dynamics of this layer cannot be separated from the layers above and below. Energy and momentum move vertically as well as horizontally, linking the upper troposphere to both the surface and the stratosphere. This vertical connection ensures that changes in one region influence conditions in others over time. As Rossby waves continue to evolve, they shape the broader pattern of atmospheric circulation. Their presence defines the character of the jet stream, guiding its path and influencing its strength. Through these interactions, the upper troposphere acts as a central organizing layer in the atmosphere where large-scale patterns of motion are formed and continuously reshaped. In the region where the upper troposphere meets the lower stratosphere, the atmosphere forms a transitional boundary known as the tropopause. This boundary is not a sharp line, but a gradual shift in temperature behavior and vertical stability. Below it, air tends to rise and mix through convection and storm activity. Above it, vertical motion becomes more restricted and layered. This transition zone plays a central role in guiding the flow of high-altitude winds, including the jet stream, by separating turbulent lower air from more stable upper layers. The height of the tropopause varies with latitude. Near the equator, strong solar heating causes the troposphere to expand upward, raising the boundary to greater altitudes. Near the poles, cooler conditions compress the lower atmosphere, lowering the boundary closer to the surface. This difference creates a sloping global structure that influences how air moves between regions. The sloping nature of this boundary helps channel upper-level winds along paths that follow the temperature gradient between equator and pole. Temperature behavior across the tropopause changes abruptly. In the troposphere below, temperature generally decreases with height. In the stratosphere above, temperature stabilizes and in some regions increases due to absorption of ultraviolet radiation by ozone. This reversal creates a stable layer that resists vertical mixing. As a result, air flowing horizontally near this boundary becomes more organized and faster moving, forming the core environment where the jet stream develops. The stability of the tropopause is essential for the structure of large-scale atmospheric circulation. It acts as a barrier that confines most weather systems below it, while allowing energy to be transferred horizontally along its surface. This confinement encourages the formation of strong horizontal winds rather than vertical movement, reinforcing the development of narrow, fast-flowing air currents at high altitude. Within this boundary region, small variations in temperature and pressure can have significant effects on airflow. Slight differences in heating between adjacent air masses can strengthen or weaken local wind speeds. These variations accumulate along the length of the jet stream, producing regions of acceleration and deceleration. The result is a highly dynamic flow that remains structured but constantly shifting. The tropopause also serves as a region where atmospheric waves interact strongly with stability gradients. Rossby waves traveling upward from the lower atmosphere encounter this boundary and adjust their structure. Some energy is reflected downward, while some is transmitted upward into the stratosphere. This interaction influences both the shape of the jet stream and the behavior of higher atmospheric layers. Air within this region moves primarily along horizontal paths due to the strong resistance to vertical displacement. When air parcels attempt to rise or sink, they encounter rapid changes in temperature that restore them toward their original level. This restoring effect creates a stable environment where horizontal motion dominates. As a result, energy is redistributed laterally across large distances rather than vertically. The sloping structure of the tropopause across latitudes contributes to the formation of strong temperature gradients at high altitude. These gradients are most pronounced where warm tropical air meets cold polar air. The contrast between these air masses creates pressure differences that accelerate winds along the boundary. The jet stream forms along this zone of maximum contrast, following the path of strongest thermal variation. In this region, the atmosphere behaves like a layered fluid system. Each layer has distinct properties, but they remain connected through continuous exchange of energy and momentum. The tropopause acts as a flexible interface between these layers, allowing certain forms of motion to pass through while restricting others. This selective interaction helps maintain the organized structure of upper-level winds. The jet stream itself is not fixed within the tropopause, but shifts slightly above and below it depending on atmospheric conditions. Its position is influenced by seasonal changes, temperature anomalies, and the strength of underlying waves. When temperature gradients intensify, the jet stream can become more concentrated and faster moving. When gradients weaken, it can broaden and become more diffuse. Moisture also plays a role in shaping conditions near the tropopause. As air rises from the surface and cools, water vapor condenses and releases latent heat. This release of energy can influence local stability and modify the structure of air movement near the boundary. Although most moisture remains in the lower atmosphere, its effects extend upward into this transitional region. The interaction between turbulence below and stability above creates a complex balance in the tropopause. Turbulent air from storms attempts to rise while stable air above resists mixing. This interaction produces regions of shear where wind speed changes rapidly with height. These shear zones are important for maintaining the strength and shape of the jet stream. Energy transfer across the tropopause is not continuous but occurs through wave-like processes. Disturbances in the lower atmosphere can propagate upward, carrying energy into the boundary layer. Some of this energy is absorbed while some is reflected or redirected. This process influences the long-term evolution of atmospheric circulation patterns. The structure of this boundary region remains sensitive to global changes in temperature distribution. As the balance of heat between equator and poles shifts, the position and slope of the tropopause can adjust accordingly. These adjustments, although gradual, influence the pathways of upper-level winds and the overall configuration of atmospheric circulation. In this transitional layer, the atmosphere maintains a delicate equilibrium between motion and stability. Horizontal flows dominate, but they are shaped continuously by underlying thermal contrasts and wave interactions. The tropopause serves as a guiding structure that channels energy into organized wind patterns while limiting vertical mixing. Through this balance of stability and variability, the upper atmosphere establishes the conditions necessary for the formation of persistent high-altitude currents. These currents reflect the underlying structure of temperature pressure and rotation, linking surface processes to the broader dynamics of global circulation. In the upper atmosphere above the tropopause, the stratosphere forms a layered environment where vertical motion is limited and horizontal flow becomes more structured. This region is defined by increasing stability with height, meaning that air parcels resist upward or downward displacement. Unlike the turbulent troposphere below, the stratosphere is shaped by slow, large-scale circulation patterns that evolve over longer timescales. These patterns interact indirectly with the jet stream beneath, influencing its strength and position through gradual adjustments in temperature and pressure. The stratosphere is characterized by a temperature profile that differs fundamentally from the lower atmosphere. Instead of cooling with height, temperatures increase slowly in many regions due to the absorption of ultraviolet radiation by ozone molecules. Ozone is a form of oxygen that forms a protective layer in this region, absorbing high-energy sunlight and converting it into heat. This heating creates a stable structure that limits vertical mixing and contributes to the layered nature of the stratosphere. Ozone concentration is not evenly distributed. It varies with latitude, altitude, and season. In polar regions, chemical reactions influenced by extremely low temperatures can reduce ozone levels during certain periods, creating regions of lower absorption and cooler conditions. In contrast, mid-latitude and tropical regions maintain more stable ozone concentrations. These differences contribute to temperature gradients within the stratosphere that influence circulation patterns on a global scale. The circulation of air in the stratosphere is generally slower than in the troposphere, but it follows organized patterns that span the entire hemisphere. Air rises slowly in tropical regions and moves toward the poles at high altitude, before descending in mid-latitude and polar regions. This circulation, often referred to as the Brewer-Dobson circulation, redistributes heat and chemical species across the stratosphere over long timescales. It plays a key role in maintaining the overall balance of the upper atmosphere. In polar regions, the stratosphere becomes particularly important due to the presence of the polar vortex. This vortex is a large-scale circulation system that forms during colder months when temperature differences between polar and mid-latitude regions intensify. The vortex is strongest in the stratosphere, where it forms a coherent ring of circulating air that helps contain cold air within high latitudes. Its strength and stability influence conditions in the lower atmosphere, including the behavior of the jet stream. When the polar stratospheric vortex is strong, it tends to isolate cold air more effectively. This isolation strengthens the temperature gradient between polar and mid-latitude regions, which can enhance wind speeds in the upper troposphere. When the vortex weakens, this containment becomes less effective, allowing energy and momentum to redistribute more freely across latitudes. These changes can influence the structure of the jet stream over periods ranging from days to weeks. The stratosphere also interacts with upward propagating waves from the troposphere. These waves carry energy and momentum into higher altitudes where they can modify the structure of the circulation. When wave activity is strong, it can disturb the polar vortex, leading to changes in its shape and intensity. These disturbances do not occur instantly, but develop over time as energy accumulates and redistributes within the system. Temperature gradients within the stratosphere are generally weaker than those in the troposphere, but they remain important for maintaining circulation. Small changes in temperature can influence the stability of air masses and the direction of the large-scale flow. Because the stratosphere is more stable overall, even subtle variations can have long-lasting effects on atmospheric structure. Vertical mixing in the stratosphere is limited due to strong stability. Air parcels that attempt to move vertically encounter restoring forces that return them to their original level. This restriction helps preserve the layered structure of the region and allows chemical species such as ozone to remain concentrated in specific altitude ranges. It also slows the exchange of air between the stratosphere and troposphere, creating a distinct separation between the two layers. The interaction between stratospheric circulation and the jet stream occurs indirectly through changes in temperature distribution and wave propagation. When stratospheric conditions shift, they can alter the way energy is transmitted downward into the troposphere. These downward influences can modify the position and strength of the jet stream over time, even though the two regions remain physically separated. Seasonal changes have a strong effect on the stratosphere. During winter, polar regions experience long periods of darkness, leading to strong cooling and the development of a stable vortex. During summer, increased solar radiation warms the upper atmosphere and weakens the vortex structure. These seasonal cycles drive regular changes in stratospheric circulation that influence conditions below. Sudden disturbances in the stratosphere can occur when wave energy from the lower atmosphere becomes particularly strong. These disturbances can lead to rapid warming events in polar regions, where temperatures increase significantly over a short period. Such events can disrupt the structure of the polar vortex and alter circulation patterns throughout the stratosphere. These changes often propagate downward, affecting weather patterns in the troposphere. The stratosphere acts as a slowly evolving reservoir of atmospheric energy and structure. While changes occur more gradually than in lower layers, their effects can be widespread and persistent. The interaction between radiation chemistry and circulation creates a system that influences the entire atmospheric column above and below it. Through its layered stability and slow circulation, the stratosphere plays a central role in shaping global atmospheric dynamics. Its connection to the jet stream is indirect, but significant, mediated through temperature gradients, wave interactions, and long-range circulation patterns that extend across the hemisphere. Across the ocean basins of the planet, the atmosphere interacts continuously with vast reservoirs of water that store and release heat over long periods. The ocean surface does not respond instantly to changes in solar energy. Instead, it absorbs heat slowly during warmer periods and releases it gradually during cooler periods. This delayed response creates persistent temperature patterns across large regions of the sea surface. These patterns influence the air above, shaping pressure systems and altering the flow of upper-level winds, including the jet stream. Ocean currents transport warm and cold water across great distances. Warm currents moving away from equatorial regions carry energy toward higher latitudes, while cold currents return cooler water toward the tropics. These movements create a complex network of heat exchange within the ocean. The atmosphere above responds to these patterns through changes in evaporation, humidity, and temperature gradients. Where the ocean is warm, air tends to rise more easily due to increased moisture and heat transfer. Where the ocean is cold, the air remains more stable and dense. The boundary between ocean and atmosphere is a dynamic interface where energy is constantly exchanged. Heat flows from the ocean into the air through conduction and evaporation, while momentum is transferred through wind stress on the surface. This interaction shapes weather systems and influences the development of large-scale atmospheric circulation. Over time, persistent ocean temperature patterns can reinforce or weaken atmospheric flow structures. One of the most influential oceanic processes is the variation in sea surface temperature across the tropical Pacific. These variations occur over cycles that can last months to years, altering the distribution of heat across the ocean surface. When warm water accumulates in certain regions, atmospheric convection above those areas becomes stronger, influencing global wind patterns. When cooler conditions dominate, convection weakens and atmospheric circulation adjusts accordingly. These shifts can extend their influence far beyond the tropics. The atmosphere responds to ocean temperature patterns through changes in pressure distribution. Warm ocean regions tend to generate rising air and lower surface pressure, while cooler regions are associated with sinking air and higher pressure. These pressure differences drive large-scale wind patterns that extend into the upper troposphere. The jet stream located higher in the atmosphere responds indirectly to these changes through adjustments in temperature gradients and wave structures. Oceanic heat storage also influences the timing and intensity of atmospheric variability. Because the ocean releases heat slowly, it can sustain atmospheric anomalies over extended periods. This persistence allows patterns in the atmosphere to develop gradually and maintain themselves longer than they would in the absence of ocean influence. The interaction between ocean and atmosphere therefore introduces a memory effect into the climate system, where past conditions continue to shape current behavior. Surface winds generated by atmospheric pressure differences also influence the ocean itself. As wind moves across the surface, it transfers momentum to the water-driving currents and mixing surface layers. This feedback loop creates a coupled system where the ocean and atmosphere continuously adjust to each other. Changes in one component lead to responses in the other, forming a tightly linked dynamic system. In mid-latitude regions, ocean temperature gradients can be particularly strong. These gradients influence storm development and the path of atmospheric waves. When warm and cold ocean regions are positioned in certain configurations, they can enhance or weaken the development of large-scale pressure systems. These systems in turn guide the flow of air aloft and shape the structure of the jet stream. The interaction between ocean and atmosphere is not uniform across the globe. Different ocean basins exhibit different patterns of variability, each contributing in distinct ways to atmospheric circulation. The Atlantic, Pacific, and Indian Oceans all play roles in shaping regional and global weather patterns. These influences combine to produce complex interactions that affect the behavior of winds at high altitude. Evaporation from the ocean surface adds moisture to the atmosphere, which later condenses to form clouds and precipitation. This process transfers energy from the ocean into the atmosphere in the form of latent heat. The release of this energy during condensation influences atmospheric stability and can enhance vertical motion in certain regions. These processes contribute to the development of storm systems that interact with upper-level winds. The distribution of ocean heat also affects the position of a large-scale atmospheric circulation cells. When ocean temperatures shift, the boundaries of these circulation cells can move, altering the pathways of air movement across the hemisphere. These shifts influence the position of the jet stream by modifying the underlying temperature gradients that drive its flow. In some cases, oceanic patterns can reinforce atmospheric wave structures. When persistent temperature anomalies align with existing atmospheric waves, they can strengthen those waves and extend their influence. This reinforcement can lead to more pronounced bending of the jet stream, affecting weather patterns over large regions for extended periods. The ocean atmosphere system operates on multiple timescales. Short-term interactions occur daily through evaporation and heat exchange. Longer-term interactions develop over seasons and years as ocean heat content changes. These longer cycles provide a slow evolving background that shapes atmospheric behavior over time. The jet stream responds to this background through gradual adjustments in its position and strength. Through continuous exchange of energy and momentum, the ocean and atmosphere form a coupled system that regulates global climate variability. The slow movement of heat within the ocean provides stability, while the faster dynamics of the atmosphere respond and adjust. This interaction creates a balance that influences the structure of winds from the surface to the highest layers of the troposphere. In the tropical belt of the atmosphere, strong solar heating drives persistent upward motion of air, creating a region of continuous convection that plays a central role in global circulation. Warm surface conditions allow moist air to rise rapidly, carrying large amounts of water vapor into higher altitudes. As this air ascends, it cools and releases energy through condensation, forming clouds and precipitation. This release of latent heat is a major energy source for atmospheric motion and helps sustain large-scale circulation patterns that extend far beyond the tropics. The tropical atmosphere is characterized by deep convection cells, where air rises in localized regions of intense heating. These regions are often associated with warm ocean surfaces where evaporation supplies abundant moisture to the atmosphere. The rising air creates zones of low pressure at the surface, drawing in surrounding air that also becomes part of the convective cycle. This continuous upward transport of energy influences the structure of winds at higher altitudes, including the formation of broad return flows in the upper troposphere. As air rises in tropical regions, it eventually reaches higher altitudes where it spreads outward toward the poles. This outward flow forms part of a large-scale circulation system that redistributes heat from equatorial regions toward higher latitudes. The movement of air at these levels contributes to the formation of pressure gradients that influence the behavior of the jet stream in mid-latitude regions. Although the tropical atmosphere is distant from polar regions, its influence extends across the entire hemisphere through these upper-level connections. The tropical atmosphere is also shaped by persistent regions of organized convection. These regions can remain active for extended periods, maintaining consistent patterns of rising air and cloud formation. Within these areas, energy transfer is highly efficient as warm, moist air continuously feeds into the upper atmosphere. The resulting circulation patterns influence not only local weather, but also global atmospheric structure through their interaction with large-scale wave systems. One important feature of tropical circulation is the presence of trade winds near the surface. These winds move toward regions of low pressure near the equator, driven by the pressure difference between subtropical high-pressure zones and equatorial low-pressure zones. As these winds converge, they enhance upward motion and reinforce convective activity. The interaction between surface winds and upper-level outflow creates a closed circulation system that links different layers of the atmosphere. At higher altitudes above tropical convection, air flows outward in broad layers toward mid-latitudes. This outflow contributes to the formation of upper-level wind patterns that eventually feed into the jet stream. The distribution of this outflow is not uniform. It varies with seasonal changes, ocean temperatures, and atmospheric stability. These variations influence how energy is transferred from tropical regions into the global circulation system. The tropical atmosphere is also a region of strong moisture transport. Water vapor plays a central role in energy exchange because it stores latent heat that is released during condensation. This process allows energy to be moved vertically and horizontally through the atmosphere. As moist air rises and cools, the release of latent heat amplifies atmospheric motion and supports the development of large-scale circulation patterns. In this region, atmospheric waves generated in the tropics can propagate outward into higher latitudes. These waves interact with mid-latitude circulation and influence the structure of the jet stream. The strength and position of these waves depend on the intensity of tropical convection and the distribution of heat across ocean surfaces. When tropical convection is strong, wave activity increases, leading to more pronounced effects on global circulation. The tropical atmosphere is also sensitive to variations in surface temperature. Small changes in ocean heat can significantly alter convection patterns, which in turn affect atmospheric circulation on a global scale. These changes can persist over time due to the feedback between ocean and atmosphere, creating long-lasting influences on wind patterns and energy distribution. The vertical structure of the tropical atmosphere is marked by strong upward motion in the lower layers and outward flow in the upper layers. This structure forms part of a global circulation system that connects the equator to the poles. The energy transported through this system helps maintain the balance between regions of excess heat and regions of energy deficit. The interaction between tropical convection and upper-level winds is continuous. As air rises and spreads outward, it modifies pressure patterns aloft. These changes influence the formation and evolution of large-scale wave structures in the mid-latitudes. The jet stream responds to these adjustments by shifting its position and strength, reflecting the influence of tropical energy input. Tropical circulation is therefore a key driver of global atmospheric dynamics. It serves as a primary source of energy for large-scale motion linking surface heating to upper-level wind patterns. Through continuous convection, moisture transport and wave generation, the tropical atmosphere contributes to the structure and variability of winds across the hemisphere. The connection between tropical processes and higher latitude circulation is gradual but persistent. Energy moves from the equator toward the poles through a combination of atmospheric flow and wave propagation. This transfer shapes the behavior of the jet stream and influences weather patterns across multiple regions. In the stratosphere above the tropics, sudden changes in temperature can occasionally disrupt the normally stable structure of the upper atmosphere. These events occur when large-scale wave energy, originating in the lower atmosphere, propagates upward and interacts with the polar circulation system. As this energy accumulates, it can alter the balance of forces that maintain the stratospheric wind patterns, leading to rapid adjustments in temperature and circulation. A sudden stratospheric warming event is one such disruption. It is characterized by a rapid increase in temperature in the polar stratosphere over a short period of time. This warming is not caused by direct surface heating, but by the downward transfer and redistribution of energy from atmospheric waves. These waves, which originate in the troposphere due to surface and weather-related processes, carry momentum upward until they break or dissipate in the stratosphere. When this happens, the normal circulation of the polar vortex can weaken or reverse temporarily. The polar vortex is a large-scale circulation system that normally helps confine cold air within high latitudes. It is strongest in winter when temperature contrasts between polar and mid-latitude regions are greatest. In the stratosphere, this vortex forms a coherent structure of circulating winds that encircle the pole. Its stability depends on the balance between radiative cooling and dynamical forcing from atmospheric waves. When this balance is disrupted, the vortex can change shape, weaken, or even split into multiple parts. During a sudden warming event, the temperature in the polar stratosphere can rise significantly over the course of days. This change occurs because wave energy forces air downward, compressing and heating it as it descends. At the same time, the normal circulation patterns that maintain cold conditions are disrupted. The result is a rapid reorganization of the upper atmospheric structure. These changes in the stratosphere do not remain isolated. They influence the lower atmosphere through a process of downward coupling. As the stratospheric circulation adjusts, pressure patterns near the tropopause shift in response. These shifts can propagate downward over time, eventually affecting the jet stream in the upper troposphere. The result is often a change in the position and strength of high-altitude winds across mid-latitudes. The relationship between stratospheric warming events and surface weather is indirect but significant. When the polar vortex weakens, the temperature gradient between polar and mid-latitude regions can decrease. This reduction in gradient influences the strength of upper-level winds, often leading to a more wavy or meandering jet stream. Such changes can persist for weeks after the initial stratospheric event has occurred. Wave activity that drives these disruptions originates from the lower atmosphere, where large-scale weather systems generate disturbances in the flow of air. These disturbances can propagate upward under certain conditions, particularly when the background wind structure allows for vertical energy transfer. Once in the stratosphere, these waves interact with the mean flow, transferring momentum and altering circulation patterns. The stratosphere responds to these inputs slowly compared to the troposphere. Its stable structure means that changes accumulate over time rather than occurring instantly. However, once a threshold is reached, the system can undergo rapid reconfiguration. This sensitivity to wave forcing makes the stratosphere a key region for understanding long-term atmospheric variability. Temperature structure within the stratosphere plays an important role in determining how energy is distributed. In polar regions, strong cooling during winter creates conditions that favor the development of a stable vortex. When wave energy disrupts this structure, the resulting changes in temperature can propagate across large regions of the upper atmosphere. The interaction between wave propagation and stratospheric circulation is influenced by seasonal timing. During winter, stronger temperature gradients and wind structures allow for more efficient upward wave transmission. During other seasons, these pathways are less favorable, and the influence of wave activity on the stratosphere is reduced. This seasonal dependency contributes to the variability of sudden warming events. When the polar vortex weakens, the effect can extend downward into the troposphere over time. This downward influence alters pressure distributions, which in turn affect wind patterns at lower altitudes. The jet stream may respond by shifting its path, becoming more amplified or slowing in certain regions. These changes can influence the development and movement of weather systems across continents. The stratosphere therefore acts as a mediator between upper atmospheric processes and surface weather. It integrates wave energy from below and redistributes it across large scales. Although changes occur slowly, their impact can be widespread due to the connected nature of atmospheric layers. Sudden stratospheric warming events illustrate the sensitivity of the atmospheric system to wave interactions. Small changes in energy transfer from the lower atmosphere can lead to significant reorganization of circulation patterns in the upper atmosphere. These reorganizations then propagate downward, demonstrating the interconnected nature of the atmospheric column. Through this process, the stratosphere influences the jet stream indirectly but powerfully. Its role is not to generate surface weather directly, but to modulate the conditions under which large-scale atmospheric circulation develops. The result is a system where disturbances at one level can cascade through multiple layers, shaping the behavior of winds across the hemisphere. Within the upper troposphere, the jet stream takes shape as a concentrated band of strong winds flowing around the hemisphere. Its structure is not uniform but varies in width, speed, and position, depending on the surrounding atmospheric conditions. This band forms where temperature gradients are strongest, particularly along the boundary between warm tropical air and cold polar air. The resulting flow is fast, narrow in some regions and more diffuse in others, reflecting the continuous adjustment of the atmosphere to uneven heating. The jet stream is maintained by the balance between pressure gradients and the rotation of the Earth. Air moves from regions of higher pressure toward regions of lower pressure, but as it travels it is deflected by the planet's rotation. This deflection organizes the flow into a predominantly west-east direction. The combination of these forces produces a stable yet flexible current that can extend for thousands of kilometers across continents and oceans. Within this high-altitude band, small changes in temperature distribution can lead to significant changes in wind speed. When the contrast between warm and cold air increases, the pressure gradient strengthens, accelerating the flow. When the contrast weakens, the flow slows and becomes more irregular. These changes occur continuously as the atmosphere responds to shifting surface conditions, ocean temperatures, and stratospheric influences. The jet stream does not follow a straight path. Instead, it moves in large-scale curves that reflect underlying atmospheric waves. These curves, known as meanders, form as the atmosphere attempts to redistribute energy between different regions. As air moves along these curves, it carries heat poleward and cold air equatorward, helping to maintain global energy balance. The shape of these meanders changes over time, influenced by both internal atmospheric dynamics and external forcing. Embedded within the jet stream are regions of faster and slower wind speeds. These variations create zones of shear where adjacent air masses move at different velocities. Shear regions are important for the development of atmospheric disturbances, as they can enhance instability and promote the growth of waves. These waves can evolve into larger patterns that influence weather systems below. The jet stream is closely linked to the structure of Rossby waves in the upper atmosphere. These waves shape the path of the flow, causing it to bend northward and southward. The interaction between wave motion and the mean flow of the jet stream creates a dynamic system in which energy is continuously transferred between scales. As waves grow, they can slow the progression of the jet stream, leading to persistent weather patterns in certain regions. In some cases, the jet stream becomes highly amplified with deep northward and southward excursions. These amplified patterns can lead to the development of blocking conditions where the flow becomes stagnant over a region for extended periods. During such conditions, weather systems can remain in place longer than usual, leading to prolonged periods of similar weather characteristics in affected areas. The position of the jet stream shifts seasonally in response to changes in solar heating. During warmer months, it tends to move poleward and weaken slightly as temperature gradients decrease. During colder months, it shifts equatorward and strengthens as contrasts between polar and tropical regions increase. These seasonal migrations reflect the atmosphere's continuous adjustment to the distribution of solar energy. The jet stream also responds to changes originating in the stratosphere. When the polar vortex strengthens or weakens, the resulting changes in temperature and pressure can influence the structure of the flow below. These influences propagate downward over time, modifying the path and strength of the jet stream. The connection between the stratosphere and the jet stream is indirect, but persistent, mediated through temperature gradients and wave interactions. Storm systems in the mid-latitudes are guided by the jet stream. These systems form along boundaries between air masses and are steered by the upper-level flow. As they move, they transport heat, moisture, and momentum across large distances. The jet stream determines their trajectory and can influence their intensity by providing regions of enhanced or reduced wind shear. The interaction between the jet stream and surface weather is continuous. As storms develop and move, they feed back into the atmospheric system by altering pressure patterns and temperature distributions. These changes in turn affect the structure of the jet stream, creating a feedback loop between surface processes and upper-level circulation. The jet stream therefore functions as both a driver and a responder within the atmospheric system. It organizes weather patterns while also being shaped by them. This dual role makes it a central feature of atmospheric dynamics, connecting processes from the surface to the upper atmosphere. Through its curved and shifting pathways, the jet stream reflects the underlying structure of global energy distribution. It acts as a channel through which the atmosphere balances temperature differences between equator and pole. Its continuous motion is a visible expression of deeper physical processes that govern the behavior of the entire atmospheric system. In mid-latitude regions beneath the jet stream, large-scale pressure systems develop as organized regions of rising and sinking air that shape weather patterns over continents and oceans. These systems are not isolated structures, but parts of a continuously evolving atmosphere where energy is redistributed through motion, temperature differences, and moisture exchange. High-pressure systems are associated with sinking air that becomes warmer and drier as it descends, while low-pressure systems are associated with rising air that cools and condenses, often producing clouds and precipitation. The formation of these pressure systems begins at the surface, where uneven heating creates regions of contrast. Land surfaces warm and cool more rapidly than oceans, producing variations in air density and pressure. These variations set air in motion, initiating circulation patterns that extend upward into the troposphere. As air rises and sinks, it organizes into rotating systems influenced by the rotation of the planet and the structure of the surrounding flow. Within these systems, air movement is guided by the balance between pressure gradients and rotational forces. As air flows toward low-pressure regions, it is deflected, causing rotation around the center of the system. This rotation organizes the system into a coherent structure that can persist for days or longer, depending on environmental conditions. These systems are embedded within the larger flow of the jet stream, which steers their movement across the globe. The interaction between pressure systems and the jet stream is continuous and dynamic. When the jet stream flows strongly and smoothly, pressure systems tend to move quickly along predictable paths. When the jet stream becomes more curved or fragmented, these systems can slow down or stall. This interaction determines the timing and location of weather events across mid-latitude regions. Storm systems develop when areas of low pressure intensify. This intensification occurs when rising air continues to draw in surrounding air, reinforcing upward motion. As air rises, it cools and moisture condenses, releasing energy that further strengthens the system. This process creates a feedback loop in which energy from phase changes in water contributes to atmospheric motion. High-pressure systems, in contrast, are characterized by descending air that suppresses cloud formation. As air sinks, it warms and becomes less humid, reducing the likelihood of precipitation. These systems often bring clearer conditions and more stable weather. However, their interaction with surrounding systems can still influence wind patterns and temperature distributions over large areas. The distribution of pressure systems across the mid-latitudes is not random. It is influenced by the position of the jet stream and the underlying temperature gradients. Where the jet stream dips southward, colder air can extend into lower latitudes, promoting the development of low-pressure systems. Where it shifts northward, warmer air can dominate, supporting high-pressure conditions. The movement of these systems is guided by upper-level winds. The jet stream acts as a steering mechanism, directing storms along paths that follow the flow of energy in the atmosphere. This guidance is not absolute, but it provides a dominant influence on the trajectory of weather systems. Changes in the jet stream can therefore have significant impacts on regional weather patterns. In some cases, pressure systems can become locked in place when the jet stream develops strong meanders. This situation leads to prolonged periods of similar weather conditions as systems remain stationary or move slowly over the same region. These persistent patterns can influence temperature, precipitation, and wind conditions over extended periods. The interaction between pressure systems and the jet stream also affects the distribution of energy across the atmosphere. As storms transport heat and moisture, they modify the local temperature structure. These changes feed back into the larger circulation, influencing the position and strength of the jet stream. This feedback loop operates continuously, maintaining the dynamic balance of the atmosphere. Vertical structure within pressure systems is also important. Rising air in a low-pressure systems extends upward into the mid and upper troposphere, where it interacts with the jet stream. This interaction can enhance or weaken upper-level winds depending on the alignment of temperature and pressure gradients. The coupling between surface systems and upper-level flow is a key feature of atmospheric dynamics. The life cycle of a pressure system involves development, maturation, and eventual decay. During development, temperature contrasts and initial disturbances create rising or sinking motion. During maturation, the system reaches peak intensity as energy transfer is most efficient. During decay, energy is gradually dissipated as gradients weaken, and the system loses structure. Throughout this cycle, the jet stream influences the timing and path of each stage. The spatial distribution of pressure systems across the hemisphere forms a pattern that reflects the underlying wave structure of the atmosphere. These patterns are not fixed but evolve as energy is redistributed between regions. The jet stream plays a central role in shaping these patterns, guiding the formation and movement of systems across continents and oceans. Through continuous interaction between surface processes and upper-level winds, the atmosphere maintains a dynamic equilibrium. Pressure systems act as carriers of energy, while the jet stream organizes their movement. Together, they form a connected system that governs weather variability across mid-latitude regions. The behavior of these systems demonstrates the interconnected nature of the atmosphere. Changes at the surface influence upper-level winds, and changes in upper-level winds influence surface conditions. This continuous exchange ensures that no part of the system operates in isolation, but instead functions as part of a larger circulating structure. At the surface of the Earth, the effects of upper atmospheric circulation become visible through patterns of temperature extremes, storm activity, and shifting weather conditions. These surface impacts are not directly caused by the jet stream alone, but by the combined interaction of pressure systems, ocean conditions, moisture availability, and large-scale atmospheric waves. The jet stream acts as a guiding structure, shaping where energy and air masses move, while the surface responds through changes in heat, wind, and precipitation. When the jet stream becomes more amplified with deeper northward and southward curves, regions of contrasting air masses can extend farther than usual. Cold polar air can move into lower latitudes while warm tropical air can extend toward higher latitudes. This displacement alters the balance of temperature across continents, creating periods of unusually warm or cold conditions depending on the position of the flow. These shifts are part of the natural variability of the atmosphere driven by changes in wave structure and energy distribution. Storm tracks are strongly influenced by the position of the jet stream. As pressure systems form and move beneath it, they follow paths guided by upper-level winds. When the jet stream is relatively straight and strong, storms tend to move quickly across regions, producing shorter-lived weather events. When it becomes more curved or blocked, storms can slow down, intensify, or remain in place for longer periods. This variation affects rainfall distribution, wind strength, and temperature changes at the surface. Heat waves and cold outbreaks are often associated with persistent jet stream patterns. When warm air becomes trapped under a high-pressure ridge, it can lead to extended periods of high temperatures. When cold air becomes trapped under a deep trough, prolonged cold conditions can occur. These patterns are not fixed but evolve as the jet stream shifts in response to changes in temperature gradients and wave activity in the upper atmosphere. Moisture transport is another key connection between the jet stream and surface conditions. As air masses move along storm systems, they carry water vapor across long distances. When this moisture condenses, it produces precipitation that can vary in intensity depending on atmospheric conditions. The distribution of rainfall is therefore closely linked to the structure of upper-level winds, which guide the movement of weather systems and influence where moisture is released. The interaction between surface heating and atmospheric circulation creates feedback loops that influence both local and large-scale conditions. Warm surfaces enhance evaporation and convection, which can strengthen local weather systems. These systems can then interact with the jet stream, feeding energy back into the upper atmosphere. This exchange maintains a continuous cycle of energy movement between the surface and higher layers. Land surface characteristics also affect how atmospheric systems develop. Mountains can force air upward, enhancing cloud formation and precipitation on windward sides, while creating dry conditions on leeward sides. Large flat regions allow air masses to move more freely, enabling broader weather systems to develop. These surface features interact with upper-level winds, shaping the structure and evolution of atmospheric circulation. The oceans continue to play a stabilizing and modulating role in surface conditions. By storing and releasing heat over long periods, they influence the temperature gradients that drive atmospheric motion. When ocean temperatures shift, they can alter the position and strength of pressure systems, which in turn affects the jet stream. This interconnected system ensures that surface and atmospheric processes evolve together over time. Seasonal transitions are especially important in shaping surface weather patterns. As solar heating changes throughout the year, temperature gradients shift between equator and pole. These shifts influence the strength and position of the jet stream, which then alters storm tracks and pressure system behavior. The result is a seasonal cycle of changing weather patterns that reflect the underlying structure of atmospheric circulation. Extreme weather events often emerge when multiple atmospheric factors align. Strong temperature gradients, amplified jet stream patterns, and persistent pressure systems can combine to produce intense storms or prolonged stable conditions. These events are part of the natural variability of the climate system arising from the interaction of energy flows across different layers of the atmosphere. The surface atmosphere remains in constant communication with the upper levels through continuous exchange of energy, momentum, and moisture. This exchange ensures that changes in one region influence others over time. The jet stream acts as a key connector in this system, linking distant regions and guiding the movement of atmospheric disturbances across the hemisphere. As air moves through the system, it carries with it the imprint of past conditions. Heat stored in the ocean, moisture evaporated from the surface, and wave energy generated in the lower atmosphere all contribute to the evolving state of the system. This accumulation of influences creates a complex and dynamic environment where current conditions are shaped by both recent and distant processes. Through this layered interaction, surface weather becomes a reflection of larger atmospheric dynamics. The jet stream organizes these dynamics into coherent patterns, while the surface responds with localized expressions of temperature, wind, and precipitation. Together they form a connected system that spans from the ground to the upper atmosphere, maintaining continuous movement and adjustment. Across the atmosphere, long-lasting patterns of circulation can emerge when the flow of the jet stream becomes organized into persistent shapes. These shapes are not fixed structures, but recurring configurations of waves, pressure systems, and wind patterns that can remain stable for days or weeks. In some cases, the atmosphere enters a state where large-scale movement slows and energy becomes distributed unevenly across regions. This behavior is closely linked to the interaction between temperature gradients, wave activity, and the stability of the upper atmosphere. When the jet stream develops strong meanders, it can create regions where air becomes trapped within slow-moving circulation patterns. These regions can take the form of broad ridges of high pressure or deep troughs of low pressure. Within a ridge, air tends to descend and warm, leading to clearer and more stable conditions. Within a trough, air rises and cools, leading to cloud formation and precipitation. These contrasting regions can remain in place for extended periods, when the flow of the jet stream weakens or becomes blocked. Blocking patterns occur when the normal west-to-east movement of the jet stream is disrupted. In such cases, the flow can split or form closed loops that slow the progression of weather systems. When this happens, atmospheric energy becomes concentrated in certain regions while other areas experience reduced activity. These patterns can persist because the balance of forces within the atmosphere temporarily favors stability in a specific configuration. The development of persistent atmospheric patterns is influenced by the interaction between Rossby waves and the jet stream. When waves become amplified, they can slow the overall flow and create regions of stagnation. These amplified waves reflect underlying variations in temperature and pressure that extend across large distances. As energy is redistributed within these wave structures, the atmosphere adjusts by reorganizing its circulation patterns. Surface conditions also contribute to the formation of persistent patterns. When land or ocean regions maintain strong temperature anomalies over time, they can reinforce atmospheric structures above them. These anomalies influence pressure systems, which in turn affect the position and shape of the jet stream. The result is a feedback process, where surface and atmospheric conditions reinforce one another over extended periods. Moisture distribution plays a role in maintaining these patterns as well. Regions with persistent convection can continuously supply energy to the atmosphere through latent heat release. This energy influences vertical motion and can sustain atmospheric disturbances that interact with upper-level winds. When combined with stable jet stream configurations, this process can reinforce long-lasting weather patterns. The interaction between the stratosphere and troposphere can also contribute to the persistence of atmospheric structures. Changes in the stratospheric circulation can modify the position and strength of the jet stream below. When these changes align with existing wave patterns, they can reinforce certain configurations, making them more stable over time. This vertical coupling adds another layer of complexity to atmospheric dynamics. In some cases, the atmosphere can transition between different states of circulation. One state may be characterized by a strong, fast-moving jet stream with relatively straight flow, while another state may involve slower, more meandering patterns. These transitions occur gradually as energy is redistributed across the system. The atmosphere does not shift abruptly, but evolves through continuous adjustment of its internal structure. The persistence of atmospheric patterns affects the distribution of weather events at the surface. Regions under stable high pressure may experience extended periods of dryness and clear skies, while regions under persistent low pressure may experience prolonged cloudiness and precipitation. These conditions are not fixed, but depend on the evolving configuration of upper-level winds and wave structures. Energy transfer within the atmosphere continues even during periods of apparent stability. Although large-scale movement may slow, smaller-scale processes remain active. Localized convection wave propagation and moisture exchange continue to redistribute energy within the system. These processes ensure that the atmosphere remains dynamic, even when large patterns appear stationary. The structure of the jet stream during these periods reflects a balance between competing forces. Temperature gradients attempt to drive motion, while wave interactions and pressure systems shape the resulting flow. When these forces reach a temporary balance, the atmosphere can maintain a stable pattern for extended periods before gradually shifting into a new configuration. The variability of atmospheric patterns is a natural outcome of a complex system with multiple interacting components. No single factor determines the structure of the jet stream or the distribution of weather systems. Instead, the behavior emerges from the continuous interaction of temperature, pressure, moisture, rotation, and wave dynamics across the entire atmosphere. As these processes continue, the atmosphere cycles through different states of organization. Each state reflects a different arrangement of energy and motion, shaped by both internal dynamics and external forcing from the surface and stratosphere. The jet stream acts as a central organizing feature within this system, guiding the evolution of patterns across large distances. Through this ongoing process of adjustment and reorganization, the atmosphere maintains a dynamic equilibrium. Patterns form, persist, and dissolve, but the overall system remains in constant motion. This balance between stability and variability defines the behavior of the jet stream and the broader atmospheric circulation. Across the hemisphere, the atmosphere continues its slow and continuous adjustment as energy moves between the equator and the poles, between the surface and the upper layers, and between regions of rising and sinking air. This adjustment does not follow a fixed path, but emerges from the interaction of many overlapping processes. Temperature differences, pressure gradients, moisture exchange, and rotational forces combine to shape the flow of air in ways that evolve from moment to moment. The jet stream remains embedded within this broader system, responding to these changes while also helping to organize them. In the highest reach of the troposphere, the jet stream reflects the combined influence of all underlying atmospheric layers. Its position and strength depend on the balance of energy within the system, particularly the contrast between warm and cold air masses. When this contrast is strong, the flow becomes more concentrated and faster. When it weakens, the flow spreads out and becomes more variable. These changes occur gradually as the atmosphere responds to shifts in surface heating and upper-level dynamics. The connection between the jet stream and the surface is maintained through continuous vertical exchange. Air rises in regions of low pressure, transporting heat and moisture upward, while air descends in regions of high pressure, returning energy toward the surface. This vertical movement links weather systems to larger circulation patterns, ensuring that local changes contribute to global atmospheric behavior. The stratosphere above adds another layer of influence through slower but persistent circulation patterns. Energy transferred upward from the troposphere interacts with the stable structure of the stratosphere, where it can be redirected or absorbed. These interactions can gradually modify the temperature and wind structure above the jet stream, feeding back into lower atmospheric levels over time. The atmosphere does not operate in isolated parts. Each layer influences the others through waves, energy transfer, and pressure adjustments. Disturbances originating near the surface can propagate upward, while changes in the stratosphere can propagate downward. This bidirectional coupling creates a system where no region remains independent and every change contributes to the evolving global circulation. Within this system, the jet stream functions as both a boundary and a bridge. It separates regions of contrasting temperature while also transporting energy between them. Its curved and shifting path reflects the continuous attempt of the atmosphere to redistribute heat across the planet. As it moves, it guides storm systems, influences pressure patterns, and shapes the timing and distribution of weather events. The variability observed in the jet stream is a natural expression of atmospheric dynamics. It arises from the constant interplay between stability and instability, between organized flow and turbulent motion. This variability is not random, but follows patterns determined by the underlying physical structure of the atmosphere. Over time, these patterns shift as energy is redistributed and the system evolves. Surface conditions remain a key driver of atmospheric behavior. Ocean temperatures, land heating, and moisture availability all influence the strength of convection and the formation of pressure systems. These surface processes feed energy into the atmosphere, which is then reorganized by upper-level winds. The interaction between surface and atmosphere ensures that changes propagate across multiple scales. The atmosphere also exhibits memory through the slow adjustment of ocean and stratospheric systems. Heat stored in the ocean and circulation patterns in the stratosphere can influence atmospheric behavior over extended periods. This memory effect allows past conditions to shape present dynamics, contributing to the persistence of certain patterns and the gradual evolution of others. As the atmosphere continues to evolve, it moves through cycles of organization and reorganization. Periods of strong structured flow alternate with periods of more irregular behavior. These cycles reflect changes in energy distribution and wave activity throughout the system. The jet stream responds to these cycles by shifting its position, altering its strength, and changing its shape. Despite its variability, the atmospheric system maintains an overall balance. Energy entering from the sun is redistributed across the planet through continuous motion. This motion ensures that extreme imbalances do not persist indefinitely, even though local variations can be significant and long-lasting. The jet stream plays a central role in maintaining this balance by guiding the flow of energy between regions. In this final layer of understanding, the atmosphere appears not as a collection of separate parts, but as a single interconnected system. Each process influences others, and each change contributes to a larger pattern of circulation. The jet stream is one expression of this pattern, visible in its motion across the sky, yet deeply connected to processes extending from the surface to the stratosphere. As the system continues its endless adjustment, the flow of air remains in motion, shaped by forces that act across scales of distance and time. The structure of the atmosphere emerges from this continuous interaction, maintaining both variability and coherence within a global circulation that never fully settles but always remains in balance.